Hi everyone, we are from Group 2 and today we're gonna presentation about Lab 3, which is DC high voltage measurement and monitoring. So this is our group member, and in this lab session we have three topics, which is construct of parallel DC high voltage measurement using VC and picoscope. And then the second is configuring the procedure of setting the kit control and picoscope. And the third is comparison for analyzing the reference signal from kit control and display signal from picoscope. Okay, the first one, we present about construction of parallel DC high voltage measurement using VC and picoscope. So in this lab, we have many component name, which is we use in this lab. The first one is PVT, and the second is CM measuring capacitor, and we have grounding switch and discharge and grounding rod. Also, we have electrode, connecting rod, connecting cup, floor pedestal, high voltage diode, smoothing and energy storage capacitor, and measuring resistance. Then we have insulating support, and the last we have space bar and parallel wave tail resistor. So this is our construction in lab 3. After we connect the circuit, we must make sure the grounding system is connected properly. And the circle red one is connect of braid copper cable from floor pedestal that's holding 100 picofarad and secondary unit for AC, and also floor pedestal that holding 280 ohm and secondary unit for DC. Next, for THR connect of AC and DC parallel high voltage measurement, the blue one is AC. It's the secondary capacitor connect with CM measuring capacitor. And the pink one is DC secondary capacitor connect with RM measuring resistor. And this is the step of connection for secondary capacitor. First, connect secondary capacitor with BNCF to banana connector M. Then we connect with the ground cable. Next, we connect the coaxial cable from CM measuring capacitor to BNC banana connector. Also, continue connect BNC T junction in the other side of secondary capacitor and take other coaxial cable connect BNC junction with PM1. And the last is coaxial cable connect the other side of BNCT junction with picoscope.
Hi, my name is Wong. Now I will talk about safety rule and the safety rule action that need to be concerned at the evening switch. So before we do this, we need to wear safety hand and pick grounding load, move in the path. And the first safety rule is we need to do two step. This is for discharge sequence double grounding. After turning off the power supply, personnel must first use a portable manual discharge load to touch the K connecting cup of the measuring capacitor CM and measuring resistor RM column. This slowly and safely dissipate the stored electrostatic energy through the load internal damping resistance. And the next is visual verification of the switch state. Always visually confirm that the opening switch is fully closed and physically touching the EL electrode before entering the testing enclosure. Never rely solely on control panel indicators. And this is the clean testing layout. it it have two ways to clean the testing layout. The first is physical perimeter barrier safety cage and clearance and spacing zone. And for the physical perimeter barrier, the high voltage test area is fully isolated by a grounded lead steel mesh safety enclosure. These physical cage create a distinct boundary between the high voltage hazardous testing zone and the low voltage safe control area when operator handle the picoscope and PC. And the next is the clearance and spacing zone. All high voltage equipment, including the measuring capacitor, measuring resistor, and smoothing capacitor, are positioned deep inside the cage to maintain a strict, safe air clearance distance from the mesh wall. This layout prevents high voltage flush over to the grounded safety fence.
My name is Muhammad Fahana bin Fauzi. I will say about configuration, the procedure of the setting, the kits control and picoscope. First slide is features and function of control kit 4.0. This is a source control, which is a frequency converter. The function is the main interface to operate the and manage the frequency converter. Next, the function as a master switch high voltage on or off for the high voltage generation. Also, precise the control over the output voltage level and frequency setting. This is provide a soft starter features to the increase voltage gradually and safely. For the next slide is primary side of the transformer. The function is monitoring the input primary parameter from the frequency converter and display the real time voltage and current of the primary winding. Ensure the input source is stable before the stepping up to the high voltage. This is a system monitoring of secondary side. First, monitor the high voltage output side, and then have features 8 modular slot for various measurement parameters used to display V peak, VRMS, and other DC and AC characteristic. For AC input, one physical channel have two monitoring slot at FC, which is VM1 and VM2. For DC input, one physical channel have one monitoring slot at FC, which is VM3 until VM6.
Okay, my name is Muhammad Shatatif Garizam. My biometric is P1124102001. So, next I will present the feature of function of control kit for alarm system. The control kit 4.0 include on an alarm system to improve safety during operation. It provides visual and audio warning when fault occur and can automatically shut down the system during overvoltage, overcurrent, or emergency situation. Next, the slide show the calibration step setup for both DC and AC measurement. The voltage divider must be configured using the catalog with the matching serial number to ensure accurate and reliable measurement result. For the picoscope setup, we use the Picoscope 3000 series software. Channel software. Channel A is configured for DC measurement, while channel B is configured for AC measurement. The voltage divider ratio and measurement range are set according to the catalog before saving the customer setup. Thank you.
This slide displays the calibration result for the positive DC output voltage. Here, we evaluate the system across 5 different output settings, scaling from a low initial level up to full capacity. If you look at the table, we mapped the output voltage percentage against the actual physical measurements. For instance, at a minimal 7% output, our kit control reference reached 9.717 kilovolt, while the digital display show 9.66 kilovolt, giving us a very small percentage error of just 0.59%. As we ramp up the system to its peak at 100% output, the reference voltage reached a massive 133.26 kilovolt. The display tracked this incredibly closely at 132.99 kilovolt, resulting in an error of only 0.2%. The key takeaway from this dataset is the remarkable consistency of the instrumentation. Across the entire voltage sweep, the percentage error never exceeded 0.8%. This indicates a highly linear and reliable tracking response between our high voltage control kit and the monitoring display. To understand exactly how those error margins were determined, let's look at the mathematical verification on this slide. We utilize the standard percentage error formula, which is the absolute difference between the reference voltage and the display voltage, divided by the reference voltage and multiplied by 100 to get the percentage. On the left side of the slide, you can see the step-by-step calculation for the lower operational range. For example, at 35% output, the formula processes a reference of 49.892 kilovolt and a display value of 50.29 kilovolt. Because the display reads slightly higher than the reference, it yields a negative error of negative 0.80%. On the right side, we look at the higher operational limits. At 70 output, at 70% output, the discrepancy drops to just negative 0.02%. Breaking down the math explicitly, like this confirm that our data collection is solid and verifiable. It proves that the small errors we see aren't random fluctuation, but rather minor, predictable variations well within an acceptable calibration tolerance. Okay, finally, let's look at the comprehensive summary comparing our overall reference and display values, specifically looking at our AC and DC channel alongside their established divider ratios. For channel A, which handled the AC measurements, we recorded a reference voltage of 22.342 kilovolts against a picoscope display voltage of 22.69 kilovolt. This presents a minor underestimation error of negative 2.92%. For channel B, our DC measurement channel, the reference was 28.331 kilovolt compared to a picoscope reading of 29.7075 kilovolt, which show a slight overestimation error of 5.01%. Crucially, to this setup are the divider ratios shown in the fourth column. To safely step down this high voltage for signal processing, the divider ratio were calibrated to 19651.1 for the AC channel and 20414.4 for the DC channel. In conclusion, both channels demonstrate strong alignment, while channel B approached a 5% variance. Both remain well within safe operational tolerance for high voltage testing equipment, validating our measurement setup.
On this slide, we can see the primary reason why the voltage value displayed by the picoscope different from the reference value shown by the kit control. The first factor is AC coupling setting. Since the channel E is configured in AC coupling mode, the oscilloscope removes the DC component of the signal and only measures the AC ripple. As a result, the display RMS voltage drops significantly to around 21.69 kV. The second factor is the divider ratio mismatch. The The certified divider ratio should be 20414.4, but during the test it was changed to 19651.1. Since the picoscope calculates high voltage by multiplying the measured low voltage signal with this ratio, any change directly affects the display voltage. The third factor is the oscilloscope sensitivity setting. The input range is set to 20 volt. If the radio signal from the voltage divider does not fully utilize the ADC range, quantization and resolution error become more significant and are magnified after scaling back to high voltage value. In conclusion, accurate high voltage calibration requires DC coupling model, the correct certified under ratio of 20414.4, and an appropriate oscilloscope sensitivity range. These settings help minimize uncertainty and ensure reliable measurement results.